Somewhere in the hills outside Hefei, China, engineers just recreated the core of the sun. Not metaphorically, not in a simulation, an actual superheated plasma loop, hotter than the center of our star, contained by magnets and held there for over 1,000 seconds. That's not a typo. And no, this isn't science fiction. While the rest of the world argues about pipelines and gas prices, China has quietly been building an entire ecosystem of energy sources so advanced, so absurdly scaled, that some of them shouldn't even be possible yet. Grab a seat, because this one gets weird fast. East, the artificial sun. Let's start with the one that sounds like it came straight out of a comic book. It's called East, the Experimental Advanced Superconducting Tokamak, and it lives inside the Institute of Plasma Physics in Hefei Anhui Province. Everyone just calls it China's artificial sun, which, honestly, is a pretty great nickname as far as physics experiments go. Better than most band names, too. I'd watch that concert. Here's what East actually does. It uses a massive donut-shaped magnetic chamber to trap a superheated cloud of plasma, and it heats that plasma to temperatures north of 100 million degrees Celsius. For context, the core of our actual sun runs at around 15 million degrees. So, this machine, sitting in a lab in eastern China, is running nearly 7 times hotter than the thing that keeps our entire solar system alive. Somebody clearly wasn't satisfied with just copying nature. They wanted to one-up it. Classic overachiever move. The goal is nuclear fusion, the same reaction that powers every star in the sky, the process of smashing light atomic nuclei together so hard they fuse into heavier ones and release a staggering amount of energy in the process. Unlike the fission reactors running in nuclear plants today, fusion produces no long-lived radioactive waste it can't melt down, and the fuel source is essentially deuterium pulled straight from seawater, which means the fuel supply is, functionally, limitless. You could power human civilization for millions of years off what's already dissolved in the ocean right now. No drilling required. The catch has always been containment, keeping plasma that hot, that stable, for long enough to actually harvest usable energy from it is one of the hardest engineering problems humans have ever attempted. For decades, fusion has been the technology that's permanently 30 years away. It's basically the flying car of the energy world, the thing everyone promises and nobody delivers. Except apparently somebody just did. In January of 2025, East sustained that superheated plasma loop for 1,066 seconds, over 17 minutes, smashing its own previous world record and doubling what most other reactors on Earth have managed. Superconducting magnets cooled to near absolute zero hold the plasma in place using magnetic fields strong enough to keep a cloud of matter hotter than a stellar core from ever touching the reactor walls. If it touched the walls, by the way, it would vaporize them instantly. So, precision matters here. This is not a machine you want to run on a hunch. This isn't commercial power yet. Nobody's charging their phone off East, and no, you can't buy a plug adapter for it on Amazon. But every second of stable containment is a data point pushing fusion from theoretical curiosity toward actual grid technology. And China isn't stopping at East. They're already building a follow-up reactor designed explicitly to bridge the gap toward commercial fusion power plants, and they've reportedly set their sights on having a demonstration fusion plant feeding real power into the grid sometime around 2035. While other nations are still debating funding proposals in committee rooms, China's treating this like a done deal that just hasn't finished cooking yet. And it's not just East carrying the fusion torch alone. Chinese researchers have also been pouring money into private fusion startups, something that barely existed in the country a decade ago, backed by state funding that dwarfs typical venture capital rounds. It's the kind of coordinated push where government labs, universities, and private companies are all racing toward the same finish line at the same time, instead of quietly competing against each other for scraps of funding. Thorium molten salt reactor, Gobi Desert now. if fusion feels a little too far off for your taste, China's got a nearer term answer sitting out in the middle of the Gobi Desert. And this one's arguably even wilder because it's already running right now, today. In the city of Wuwei in Gansu province, China switched on the world's first operational thorium-based molten salt reactor back in 2023. And here's the fun part. This technology isn't new. American scientists at Oak Ridge National Laboratory built and ran a working prototype of this exact concept back in the 1960s. Then the US shelved it, largely because thorium reactors don't produce the kind of weapons-grade byproducts that Cold War-era nuclear programs actually wanted. Uncle Sam looked at a reactor that couldn't melt down and couldn't be weaponized and said, pass. China looked at the same blueprint 60 years later and said, actually, that sounds perfect. We'll take it. Sometimes the best ideas just need a country willing to actually finish the homework. So what makes this reactor different? Instead of solid uranium fuel rods sitting in water, this design dissolves thorium fuel directly into a molten fluoride salt that circulates through the reactor core at extremely high temperatures, but at normal atmospheric pressure. That last part matters enormously. Traditional reactors run at intense pressure, which is exactly why a stuck valve or a power failure can spiral into catastrophe. This reactor doesn't have that problem because there's no pressure buildup to begin with. No pressure, no explosion. Simple math. And it has a built-in safety valve that sounds almost too simple to be real. At the bottom of the reactor sits a plug of frozen salt, kept solid by an active cooling fan. If the power ever cuts out, that fan stops, the plug melts, and gravity does the rest. The molten fuel drains straight into a passively cooled containment tank below, where it solidifies and simply stops reacting. No emergency systems, no human intervention, no backup generators required, just physics doing the job on its own. It's basically a reactor that knows how to shut itself down without anyone telling it to, which, frankly, is more than I can say for most of my houseplants. Thorium itself is roughly 3 to 4 times more abundant in the Earth's crust than uranium, and China happens to be sitting on some of the largest reserves on the planet, a lot of it showing up as a byproduct of the rare earth mining they're already doing anyway. So this isn't just a safer reactor design, it's a fuel source that solves China's uranium import dependency in one single move. The 2 megawatt Wuwei plant is a proof of concept for now, but Beijing has already greenlit a 10 megawatt successor, with commercial scale thorium plants reportedly on the roadmap for the 2030s. There's also something almost poetic about where this reactor sits. The Gobi Desert isn't exactly known for abundant water, and most nuclear designs need enormous volumes of it for cooling. A molten salt reactor sidesteps that problem entirely, which means China can build these things in dry, remote, sparsely populated regions instead of clustering them along coastlines like traditional plants. That's not a small detail. It means the reactor can go basically anywhere, deserts included, without fighting over water rights with farmers and cities. Baihatan and the megadam empire. Let's come back down from nuclear physics for a second and talk about something a little more old school, because China didn't abandon hydropower while chasing fusion and thorium. They just kept building it at a scale that makes the rest of the world look like it's still cranking water wheels by hand. The Baihatan Dam sits on the Jinsha River, straddling the border between Sichuan and Yunnan provinces, and it's now the second largest hydropower station on Earth, trailing only its own big sibling, the Three Gorges Dam, which still holds the top spot. Baihatan alone generates about 16,000 megawatts of capacity, which is enough electricity to power tens of millions of homes, and this is one dam, on one river, in one country that has dozens of similar megaprojects scattered across its western provinces like it's collecting them. What makes Baihatan an engineering nightmare in the best possible way is where it's built. This region sits in a seismically active zone, hemmed in by steep canyon walls, which meant engineers couldn't just pour a straightforward gravity dam and call it a day. Instead, they built a double curvature concrete arch dam, a design that uses the canyon's own rock walls to help brace the structure, distributing the immense pressure of the reservoir outward into the surrounding mountainside rather than relying purely on the dam's own mass. The structure stands about 289 meters tall, roughly the height of a 90-story skyscraper, laid flat and turned sideways into a wall holding back an entire river. And they didn't use ordinary concrete either. Engineers developed a specialized low heat cement mix specifically because standard concrete generates so much internal heat while curing that it can crack under its own thermal stress at this scale. We're talking about a pour so massive that the chemistry of concrete curing became its own multi-year engineering study. They basically had to invent a new recipe just so the dam wouldn't crack itself apart from the inside. Baking a cake at this scale would also require some serious recalculating, just saying, and probably a much bigger oven. 16 turbine generating units sit inside the dam, each one individually rated at a full gigawatt of capacity, making them the most powerful single hydro turbines ever installed anywhere on the planet. And this dam isn't a standalone flex. It's one node in a cascade of hydropower stations running down the Jinsha and Yangtze River systems, all networked together, all feeding into a grid that has to move that power somewhere useful. Which, conveniently, brings us to the next problem China had to solve: ultra-high voltage transmission. Here's the thing nobody talks about when they talk about mega energy projects. It doesn't matter how much power you generate if you can't actually move it anywhere. You can build the biggest dam or the fanciest solar farm in the world, but if it's sitting in a remote province 1,000 miles from the cities that need the electricity, you've basically just built a very expensive paperweight. China solved this with ultra-high voltage transmission, UHV for short, and it is, without exaggeration, one of the most underrated engineering achievements on the planet, mostly because power lines just aren't as photogenic as a golden sphere hotel or a spaceship-shaped building. Nobody's making videos about transmission towers, except apparently me, right now, at this exact moment. UHV lines carry electricity at voltages above 800 kilovolts for direct current systems, sometimes exceeding a full million volts, which allows power to travel thousands of kilometers with dramatically reduced transmission loss compared to conventional grids. China has built out a UHV network stretching across the entire country, moving hydropower out of Sichuan and Yunnan, wind power out of Inner Mongolia, and solar power out of the Gobi Desert, straight into the industrial hubs and megacities along the eastern coast, places like Shanghai, Guangzhou, and Beijing, where the actual demand lives. Some of these transmission corridors span over 3,000 kilometers in a single unbroken run, using towers engineered to handle electrical loads that would arc and fail on conventional infrastructure. The insulation technology alone required years of material science research, because at these voltage levels, air itself can become a conductor if you're not careful, and that's the kind of mistake that doesn't give you a second try. The result is a national grid that functions less like a patchwork of regional utilities and more like a single continent-spanning circulatory system, pumping energy from wherever it's abundant to wherever it's needed in real time at a scale no other country has attempted to replicate. It's the invisible backbone making every other project on this list actually useful, rather than just impressive on paper. You never see it, but without it, none of this works. Desert solar. Megabases. Now, let's talk about the part of this story that you actually can see from space, because China took some of its most useless land on the map and turned it into some of its most valuable. Out in the Kubuki Desert in Inner Mongolia and across sprawling stretches of the Gobi, China has been building solar installations so large that solar farm almost feels like the wrong phrase for it. These are solar bases sprawling across tens of thousands of hectares, some individual installations pushing past 1,000 megawatts of capacity on their own. One project in Kubuchi was even built in the shape of a giant galloping horse when viewed from satellite imagery, because apparently if you're going to install millions of solar panels across a desert, you might as well make it art while you're at it. Efficient and aesthetic. Somebody in that planning meeting had a sense of humor. The engineering challenge here isn't really about the panels themselves. It's about the environment they're sitting in. Desert conditions mean sandstorms, extreme temperature swings, and punishing UV exposure that degrades standard equipment far faster than it would in a temperate climate. Engineers had to develop specialized mounting systems and dust-resistant coatings just to keep these installations functional across their intended lifespan. And maintenance crews run automated cleaning robots across the panel fields because manually washing a solar farm the size of a small country is, understandably, not something anyone signed up for on their first day. There's a secondary effect happening here too, and it's honestly the more interesting part. The shade cast by rows of solar panels reduces ground evaporation and wind speed at the surface, which has allowed vegetation to take root in areas that were previously pure, shifting sand dunes. China has been explicitly using these solar installations as a tool for desertification control, essentially turning a renewable energy project into a land reclamation project at the same time. You're generating electricity and holding back the desert with the exact same infrastructure. That's the kind of two-for-one deal that doesn't usually show up in engineering textbooks. China's total installed solar capacity now dwarfs every other country on Earth combined, and a huge share of that growth has come from exactly these kinds of mega bases, engineered specifically to convert land nobody wanted into a power source nobody can afford to ignore. Offshore wind giants. If the desert was the empty canvas, the ocean turned out to be the next frontier, and China went after offshore wind with the exact same why build one when you can build the biggest energy that shows up everywhere else on this list. Off the coast of Fujian province, in waters known for brutal typhoon conditions, China has been installing some of the largest wind turbines ever constructed by human beings. We're talking single turbines with blade spans wider than a football field, rated at 16 megawatts or more per unit, meaning one single turbine can power roughly 36,000 households on its own. One turbine, spinning in the ocean, producing more power than entire small towns need in a full year. Try explaining that to a windmill from the 18th century. Building anything out here is a fight against the water itself. Engineers had to design foundation systems capable of surviving typhoon-force winds and violent wave action, while also resisting saltwater corrosion that would eat through standard steel components within a matter of years. The blades themselves use carbon fiber composite designs specifically engineered to flex under extreme wind loads without snapping, because a rigid blade in a typhoon is a blade that's about to become very expensive debris flying at high speed. Installation alone required specialized heavy lift vessels capable of hoisting turbine components the size of office buildings out into open water and setting them down onto foundations anchored dozens of meters below the surface, all while accounting for currents, tides, and a coastline that regularly gets hammered by some of the strongest storms on the planet. It's basically underwater and offshore construction happening simultaneously, in a location that seems actively determined to destroy whatever you build there. China now operates the largest offshore wind capacity of any country on Earth, and Fujian in particular has become something of a proving ground, a place where turbine manufacturers test increasingly extreme designs specifically because if a turbine can survive out there, it can survive pretty much anywhere else on the planet. Grid-scale battery storage. Here's the problem with wind and solar that nobody likes to bring up at parties. The sun sets every single day, and the wind doesn't always blow on schedule no matter how badly you need it to. You can build the most impressive renewable infrastructure on Earth, and it still won't matter if you can't store that power for the moment's demand doesn't match supply. China's answer has been to build battery storage at an absolutely relentless pace, and one of the more clever moves has been leaning hard into sodium-ion battery technology as a genuine alternative to lithium for grid-scale applications. Sodium is roughly 1,000 times more abundant in the Earth's crust than lithium, and it doesn't carry the same supply chain baggage, no scrambling for rare mineral deposits in politically unstable regions on the other side of the planet. Companies like CATL have been rolling out sodium-ion battery installations specifically designed for grid storage, where the slightly lower energy density compared to lithium doesn't matter nearly as much as it would in, say, an electric car, because these batteries aren't going anywhere. They just sit there, storing power, being reliable, completely unbothered by the drama. Beyond batteries, China has also been building out compressed air energy storage facilities, essentially massive underground caverns where excess electricity is used to compress air, which gets released later to spin turbines and generate power on demand. One facility in Hubei province can store enough compressed energy to power hundreds of thousands of homes for hours at a stretch, functioning like a giant mechanical battery buried underneath an entire mountain, quietly waiting. The overall strategy here is what actually makes everything else on this list work as a functioning grid instead of a collection of impressive but unreliable power sources. Storage is the unglamorous piece nobody puts in a highlight reel, but it's the thing that turns "we built the world's biggest solar farm" into "we built a power grid that actually stays on at night." And China's been throwing resources at that unglamorous piece like it's the most exciting project on the entire list, because in a lot of ways, functionally, it kind of is. The hydrogen play. And then there's hydrogen, the wild card that's supposed to clean up the parts of the economy that batteries and solar panels simply can't touch. Steel production, heavy shipping, long-haul trucking, industries that need serious concentrated energy, not just a trickle from a wall outlet somewhere. China has been building out green hydrogen production hubs at a pace that's honestly starting to sound familiar by this point in the video. Massive electrolysis facilities, many of them powered directly by those same desert solar farms and wind installations we just talked about a few minutes ago, split water molecules into hydrogen and oxygen using renewable electricity instead of fossil fuels, producing what's called green hydrogen, as opposed to the carbon-heavy hydrogen typically derived from natural gas. One production hub in Inner Mongolia is designed to become one of the largest green hydrogen facilities on the entire planet, feeding directly into industrial applications and a growing hydrogen pipeline and transport network built to move it from where it's made to where it's actually needed. China's also been aggressively deploying hydrogen fuel cell trucks and buses in select cities, treating heavy transport as the proving ground before hydrogen potentially scales into broader industrial use across the country. The bigger play here is strategic. Hydrogen gives China a way to store and transport renewable energy in a form that doesn't require the grid at all. A chemical battery you can literally put on a truck and ship somewhere else entirely. It's still an emerging piece of the puzzle, more construction in progress than finished product right now. But the infrastructure going into the ground at this exact moment suggests Beijing isn't treating hydrogen as some side experiment. They're treating it as the missing piece that connects everything else on this list together. Closing, the energy endgame. So step back for a second and look at what's actually happening here. A fusion reactor running hotter than the sun itself. A meltdown-proof thorium reactor pulled off a 60-year-old American shelf and actually switched on for the first time in history. The world's most powerful hydropower turbines bolted into a seismic canyon that would scare most engineers off the job. A transmission grid stretching thousands of kilometers just to move all of it somewhere useful. Solar farms the size of small nations reclaiming desert land while they generate power around the clock. Wind turbines the size of skyscrapers spinning calmly through typhoons that would flatten a normal building. Battery banks built from the most abundant element on the entire planet. And a hydrogen network quietly stitching all of it together behind the scenes. None of these projects exist in isolation. That's really the part that should keep other countries up at night if they're paying attention at all. This isn't one flashy energy bet, it's an entire portfolio built simultaneously across every available technology so that no single failure or shortage can slow the whole system down. While other nations are still arguing about which single energy source should win the debate, China just built all of them at once and let them compete for the title directly on the grid itself. And that's the real story hiding underneath all these numbers. This was never just about keeping the lights on. It's about energy independence, on a scale no other nation has even attempted. Built fast enough and big enough that by the time everyone else finishes debating the plan on paper, China will already be running on the answer.